Perfect. Good afternoon, everyone. Thank you for having me. So as introduced, I'm Lloyd Jones with APT. I'm a geochemist and petroleum systems analyst by background, and I'll be running through APT's Girasol software, which is an evaluation of wellsite gas data and how really to maximize the data that's captured on all wells. I mean, it's done really for safety reasons, and up until recently, it's really been overlooked after the drilling phase. But there's a lot of very interesting information and details you can gather with that data. So without further ado, let me share my screen and jump into the presentation. Hopefully everyone can see my screen okay. Perfect. Just grab a pointer. Right, let's get going. So what are well site gases? So well site gases in both total gas sense, so that's just a total gas recorded on an FID, and the compositional data, so that's C1 to C5 typically, but you can also get some advanced mud gas systems which go up to C8 with some aromatics there, are safety critical, and they're therefore collected on all wells at varying levels of sophistication. So that's your standard mud gas data or your advanced mud gas data. And this really has been the case since the 50s, and given that most of us work the North Sea, it's predominant that most wells in the North Sea have gas data of varying quality and vintage. So it's a massive treasure trove of data, especially looking for screening of missed pay intervals. The well site gas data is a really useful tool to very quickly screen for zones of interest. Digital data, which is what really we need and we're interested in, is typically available on wells drilled within the last 20 years, basically post the millennium. That's ideally where we start to typically see digital data. For formation evaluation, though, the gases of interest really are those released on drilling a volume of rock, and they provide the first instances of hydrocarbon saturation and the phase of the hydrocarbons you've discovered. However, there are some controlling factors on how much gas you measure on the top side, outside of the actual saturation in the rock. And the principal controls there are the hole diameter, so how big is the cylinder of rock you're cutting, how fast are you cutting the rock, so that's your ROP, and then the amount of mud flowed back to surface, that's your mud flow. And those are principally the main controls governing the amount of gas we measure at the surface. There are also other ways to add gas into the mud system. Many of these are related to how the well is drilled. So are you underbalance or overbalance? Are you inducing fractures if you're close to fracture pressure? And is there any wellbore breathing allowing mud flow back into the system when you're making a connection, for example? And these are really important to know because connection gases, trip gases, pumps off gases, etc., they'll give you really a large number of false positives in what might be interpreted as a zone of high gas when really it's just drilling related. And they can obscure the real geological gases. So typically the suite of data that you arrive at after drilling a well is you have your depth data, as you might expect, your drilling data, which I mentioned, which ROP, flow rate, and hole size are the key controls governing the amount of gas measured on the top sides of a rig. And then we have the gas data. So we have a total gas, which is just recorded continuously on an FID. And then typically we use C1 to C5 data, as that's what we're more often than not coming across against. So that's what I'll focus on here. But we do have advanced mud gas systems where you can have gases in and out, which give you an idea of any recycling of the gas within the mud system, which is a really quite important factor to know. And this chromatogram data is typically measured every 30 seconds to 45 seconds. And it's more often than not a more reliable data source than the total gas data, as they often do carbide checks within the process of drilling a well to make sure you're correctly calibrated. So how do we know the gases we're looking at are correct? And what we try and do is we normalize for the different drilling parameters. So we're trying to take away any drilling signal and maximize the geological signal that we observe in the gas data. And then we can use the normalized gas data, so both the total gas data and then a sum of the C1 to C5 components to give us a proxy total gas. We can use this to identify zones of hydrocarbon pay. In this presentation, we'll use pay in a very loose sense. So I hope there's no petrophysicists or armchair petrophysicists listening, as they might be swearing at their screens by me calling pay very loosely, as we don't provide any rock quality overprint or anything like that. This is simply pay is a loose term related to zones of increased hydrocarbon saturation. But pay is just easier to say rather than that. So that's what if you hear me say the word pay, that's what I'm referring to. So we use the total gas data to identify zones of high hydrocarbon saturation. But then we can use the C1 to C5 data to try and assess the type of the hydrocarbon phase of those zones of increased hydrocarbon saturation. The issue with the C1 to C5 data is it's very sensitive to the mud type. So are you an oil-based mud or a water-based mud? And I hope I'm speaking to a lot of geochemists will agree that an oil-based mud is their worst nightmare. And it's the same with well site gas data. It's also very tricky and hard to get around. But we can do some correction factors to try and better understand the phase of the hydrocarbon excluding the oil-based mud correction. And I've got a few slides discussing the importance of these correction factors. So this is the EEC correction factor, which I'll discuss in a few slides' time. And then we use this for a phase prediction. So is it a dry gas? Is it a volatile oil, for example? But we can also go a bit further and do some semi-quantitative GOR predictions. So the first step is to normalize the data. And I mentioned the principal controls governing the amount of gas is the hole diameter, how fast you're drilling, so the ROP, and the amount of mud flowing back to the surface, and that's your mud flow. Normalizing for drilling variables is not a new technique. There's a variety of methods that have been out there and published. Several methods require what you have to define a normal ROP or a mud flow. And if you're the operator or you're drilling back-to-back wells with the same rig, the same acquisition setup, this might be possible. But if you're drilling a different well in a different basin, how applicable really are normal ROP rates? That's one technique. There's another very detailed technique which required a full detailed quantification of the acquisition system. This did allow for a more detailed petrophysical approach to the mud to be used, and this was published in the SPE, I think around 2019, by some guys from ConocoPhillips, which is a very interesting technique, but you do require a lot of information around how you've acquired the gas. So you need to know your mud flow into the extractor, your gas suction rate, for example. This data might be available, maybe if the well was drilled last year, but if you're looking at legacy wells drilled in the 80s, for example, and you're not the operator, it's almost impossible to come by. So we found at APT, we use a simple but robust normalization method that normalizes the gas for the volume of rock cut and the volume of mud flowed to surface per unit of time. That's a very simple way we do it, and that's our normalization technique, which we believe removes any drilling signal and maximizes the geological signal of the interval drilled. Excuse me. So just show you the importance of normalization here. So this is an example from the UK sector of the North Sea, and on the left-hand plot here, this is just the total gas as recorded with depth. You can see here there are several zones of high gas that immediately that your eye immediately goes to. There's a gas peak around 4,000 feet, and then slightly deeper, 16,000 feet to 17,000 feet, two large gas peaks. And in between, there are zones of increased gas, but nothing that you'd say, right, this is a zone that I'm really interested in. It's only after you normalize it and apply a definition of what you determine to be pay, which is a background gas method, which I'll discuss on the next slide, that you start to really understand the zones that are actually interesting. So the approach we take is using a background gas method, and any gas peak 3 times larger than that background is flagged as a hydrocarbon bearing zone of potential pay, and that's what you see circled in the green here. So going down the well, there's this zone at 4,000 feet, again at 16,000 feet, 17,000 feet, but there are also some additional zones now just above 14,000 feet, and then between 8,000 and 10,000 feet. And these two zones in particular, between 8,000 and 10,000 feet, are really the interesting zones if you look at the Y-line data, as this zone just below 8,000 feet, which is only flagged as an interesting zone, as a zone of interest after the normalization process. I mean, if you look at this zone was actually tested on a DST and flowed 2,500 barrels of oil. And without normalizing the data, you'd immediately overlook that, as it's not a very interesting zone relative to the different zones of high gas in the well. So I mentioned identifying pay, and several of the normalization techniques out there can give you a very detailed quantification of the hydrocarbon saturation as they convert the gas in mud into a gas in air. And there you can do some advanced petrophysical studies, but you have to have a lot of information around the acquisition setup, which is not always available, especially at APT, where we're not an operator and we sometimes aren't privy to that type of information. So we take a slightly different approach, and we determine what pay is by identifying a zone of background gas. Typically that's in a water wet sand, or in a shale that has very low in situ gas, for example. And that's typically what we use to identify pay. And an experience has shown gas values 3 times or 4 times above this background gas level identifies the majority of petrophysical pay. And there's a link in this presentation that can take you to some work that APT published in the SPWLA comparing pay predicted from Girasol, the software that you can see on the right-hand side here, to the conventional petrophysical approaches. And that was for lateral and exploration wells for a field in the North Sea. And there's a slide towards the end of the presentation where we can discuss that in a bit more detail. And relying on gas levels to identify zones of increased hydrocarbon saturation means you can overcome some challenges that plague conventional methods. So have you had poor quality or unavailable log data? It's quite a complex logging environment, so a HPHT setting, and also some complex lithology. So in particular, the west of Shetland, the Rosebank and Cambo fields, for example, they are interbedded sands within some volcaniclastic sequences, and also low resistivity reservoirs where your lithology control is impacting your resistivity data. And you can see the example on the right-hand side here. This is from the North Sea in the UK sector. The blue polygon you see here is where the background gas has been set and at a very low level. It looks to be wet based on the wireline response as well, low gamma ray in the sand and very low resistivity. And the right-hand green column here, where my cursor is now, these are the zones where Girasol has picked up hydrocarbon pay, where your gas level is 3 times above the background, which is the black line here. And then the left-hand column here, I know the colors are pretty tricky to see around, so apologies for that. This is the petrophysical pay as determined on a CPI log. And you can see there's an excellent match between the Girasol pay and the CPI pay just here. The background gas method is used because the absolute gas levels within a well are actually quite pointless. There's a lot of external controls governing the amount of gas recorded on a rig. So the background gas method gets around this as you're using the gas peaks relative to one another. These are the 2 examples you see here. They're both from the North Sea, both for discoveries that flowed on DST, and the absolute gas levels vary significantly. So up to 12% in the upper example here, but only below 1% in the lower example here. So the absolute gas levels are relatively meaningless. It's only when you apply a background, which is the method we find most appropriate, where you start to determine zones of increased gas. So once you normalize for different drilling parameters, excuse me, I'm just going to take a drink. So once you've normalized the different drilling parameters and you've taken away any of the geological signal, taken away any of the drilling signal, you've maximized the geological signal, so you can start to determine which zones are genuine potential sands of increased hydrocarbon saturation, or is there anything in chalks or anything like that. So that's the main thing to do with drilling, and the bit I'll move on to now is the plague of most geochemist life, which is oil-based mud. So the partition of gases from the drilling mud into the air in the gas trap is directly controlled by the mud system. And the most influential aspects of data acquisition are drilling fluid type. So are you an oil-based mud or a water-based mud? The trap type, is it a constant volume trap? Is it a heated gas trap? And the actual mud return temperatures. And these 3 factors are really a massive control on the compositions of your gases that are coming out of hole. So the solubility of your C1 to C5 gases vary significantly. So C1, so methane, will readily exsolve from the gas and partition into air quite easily. But the heavier molecular weight gases, so your propanes plus, are more soluble in the oil-based mud, so they tend to stay in solution. Water-based muds, typically it's not an issue, and the gases can readily exsolve across the full molecular weights of compounds looked at. The only caveat with water-based muds is if you're in a deep water setting, so west of Shetland, for example, and you're drilling in the winter, your mud temperatures might be cold and you're not using a heated gas trap, your heavier gases will stay in solution and they will behave much like an oil-based mud if you've got a cold mud return temperature. So that's just an important caveat to do with oil-based muds. But the propensity of heavier gases to stay in solution means that uncorrected well site gas data will appear enriched in C1. So this will distort your phase prediction. So all your predicted phases will look drier and your GORs will be higher. So we use an EEC correction workflow. So EEC stands for extraction efficiency coefficient. So how easy does your compound extract from the mud? So we use this EEC correction workflow to tune the well site gas data to measured PVT compositions. This allows for any variation in gas compositions attributed to partition rates or the acquisition setup to be accounted for. Typically, we don't have access to PVT data, especially if it's a post-well evaluation and you haven't quite run your PVT samples. So we have developed a series of standard correction factors that are applicable to the North Sea, but also applicable to worldwide scenarios, really. So we have examples where your oil-based mud is just a standard oil-based mud, and you apply the correction factors there. Also, if you've got a non-heated gas trap where your mud temperature is colder, so your heavier gases will stay in solution. If you're a HPHT mud, for example, where it's the opposite, your mud is coming out of the hole hotter, so you don't need to apply as an aggressive correction. And also wells with high biogenic gas content, so that's the Gulf of Mexico is quite important. So this is just an example showing the importance of correcting for the oil-based mud. So you can see on the left-hand plot here, there's two samples, two data points. So in the blue and the orange, the blue sample is from a gas cap, and the orange sample is from the oil leg in the same reservoir. And you can see an estimated GOR had come out around 40,000 for the gas cap and around 2,000 for the oil leg. And that's with the raw compositional data. It's only when you apply the correction factor, just the default correction factor that we apply if we don't have any more information about the oil-based mud, we know that actually we're quite way off the actual PVT GORs. Once we apply the correction factor, we know that the gas GOR for the oil leg decreases and the oil leg GOR decreases too. And then the predicted GORs are then comparable to the measured PVT samples. So for the gas cap, the predicted values is around 11,000 scf per barrel, and the actual measured is just below 12,000. So quite an excellent match there. And again, if you look at the oil leg, the measured PVT GOR from the NDT sample is just under 1,100 scf per barrel, and the predicted GOR is 950. So an excellent match for the gas cap, and that's only observed once you apply the correction factors. Just go back to this slide for a second. But using this EEC correction workflow has an added advantage, as if you have PVT data available, it means you can tune your mud gas compositions to match the PVT data. So that gives you a more accurate prediction of your phase and GOR. This is particularly relevant for example, if you're in a well where you had a failed MDT run, or you had one reservoir that managed to sample some hydrocarbons to the surface, but they had an extremely high oil-based mud contamination. If you tune to a deeper reservoir where you have confidence that your measured PVT GOR is accurate, and you tune the mud gas compositions to match that PVT data point, you know that the GOR predicted in the shallower reservoir, which has the high oil-based mud contamination, is going to be accurate and gives you some confidence that you're predicting a realistic value. So I mentioned the importance of understanding the mud temperature. So this is an example from the North Sea here. It's a HPHT well, and the plot on the left-hand side is just a depth plot showing the temperature of the mud return temperature out of the hole. You can see in the 8.5-inch hole, around 4,500 meters in the reservoir zone, your mud out temperature is between 45 to 55 degrees Celsius. This is a very interesting realm of mud temperatures, as it's where you have to pay attention to if your correction factor is too aggressive. So in wells drilled with oil-based mud, but a non-heated gas trap has been used, the EEC corrections are sensitive to the temperature of the mud at the extractor. So the mud out temperature, which is what's plotted on the left-hand side, are used as a guide to this temperature. The higher the temperature, the more the heavier gases are partitioned into the airflow through the extractor. So they have exsolved from the mud and they're not staying in solution. So that's the example you can see on the left-hand side. If you're using a heated gas trap, these run at very high temperatures, typically 90 degrees Celsius, and this temperature is high enough to partition all your C1 to C5 gases readily. So you don't really need to be concerned about correction factors or oil-based muds. So everything should be as is. But if you're using a non-heated gas trap, you do have to pay attention to the mud out temperatures. So the plot here, the depth plot on the left-hand side here. This is for a well in block 27.7. And the mud out temperatures are intermediate between the standard correction factors and the hot correction factors that we've developed. And you can see on the plot here shows you the standard correction factors in blue and the hot oil-based mud correction factors in the orange, just here, and how they vary. So putting that into practice, you can see here, this is the same well from block 27.7. You see there's two zones of increased gas. They coincide with some nice sands, and they are hydrocarbon bearing, and they were tested on MDT. And using the standard correction factor that we have to use because it's an oil-based mud, it looks like we've too aggressively corrected the C1 to C5 fraction. So all our gases are too wet relative to the MDT compositions. We looked at the mud temperature. We know that the mud temperature is relatively hot, given what we typically see in the North Sea, because it is a HPHT well. So that means that we have to then use a different set of correction factors, which is not as aggressive. So we are reducing the amount of heavier hydrocarbons in the reservoir. So you can see the predicted phases here in the plot where my cursor is right now. The predicted GORs in the two sands that are the blue and orange stars are around 3,500 scf a barrel and 2,000 scf a barrel. I mean, we're predicting a gas condensate to a volatile oil, which is relatively comparable to what was actually tested on MDT. So you'd say, oh, we're relatively close, but using the oil-based mud correction factors, we know that we can get a bit closer for the HPHT setting that it is. So the predicted GORs then in the circle, in the orange, are 5,000. Sorry, there's a mix-up in the colors here. The predicted GORs then are a lot closer to the actual measured values. So this is an example showing how important the mud return temperature is. So this is an example where we're in a hot mud, but the opposite is true is if you're in colder temperatures. So your heavier gases are staying in solution, so you're not looking wetter. Your predicted hydrocarbons are looking drier. And this is currently a big part of the research within APT to understand the importance of the mud return temperatures, what they have on the correction factors that are required. This might just be depending on the operator, or it might also be depending on the actual specific type of mud you're using, and that's something we're investigating at the moment. So just a quick note on some of the future work that we're doing within APT. So we're currently using a ratio of propane to ethane to predict GORs, and that's the plot on the left-hand side here. But if you've got some confidence that your C4 and C5 data are accurate, and in legacy data sets, this is often not the case, or if you're using a standard mud gas system and a non-heated gas trap, the C4 and C5 gases are often in very low amounts and unrepresentative of what the actual formation fluid is. So using a C4, so a ratio of butane to propane and a ratio of pentane to butane, you can see a tighter clustering of a GOR trend through the three plots, and this is something we're looking at the moment. Additionally, we're also doing some work with machine learning. APT has a very large PVT database of the North Sea, so around 8,000 fluid samples, and we've leveraged this data set to investigate, to predict GORs based on C1 to C5 compositions, to predict GOR, which is what you see on the right-hand plot here, but also to go a bit further to potentially predict PSAT, formation volume factor, API, and viscosity. And I mentioned before the temperature of the mud, but the reservoir pressure and temperature also has a key control in the phase, as wellsite gases are sometimes misrepresentative in phase-separated reservoirs where you have a gas cap on an oil leg. And incorporating the reservoir pressure and temperature within the machine learning methodology gives you a more accurate prediction of the GOR. So that was everything on the actual workflow of APT's Girasol software. So highlighting the importance of normalizing for different drilling variables, and then the more important factor is understanding your oil-based mud and how you correct for that. So I'm just going to run you through a few different examples from the North Sea. Just have a drink of water first. So just got a few examples to run through. The first example is from the North Sea. And you can see this is a gas cap reservoir from the UK sector of the North Sea on a field called Leverett. This well was drilled in the late 2010s, something like that. It was gas cap reservoir with the contact being intermediate in a shale, not in the sand itself. And there are multiple stacked sands within the reservoir. And you can see 4 MDT samples were taken, and that's what the compositions in the squares are, the compositions of the MDT samples. The well was drilled with an oil-based mud, and the standard APT standard oil-based mud correction factor was used to account for the contamination of oil-based mud in the reservoir gases. And what's a quite nice example, first of all, looking at pay, you can see zones where there's sands, there's significant increases in gas, and that coincides to the hydrocarbon, the CPI saturation, sorry, on the left-hand side here. And obviously they correlate well to where you see increased resistivity. Again, we've used the background gas method to identify a water wet sand, and that's down here where we see low gamma ray and low resistivity. And then any gas peak 3 times above this background is flagged as a hydrocarbon bearing zone. And they correlate nicely to where you see low density, so you can sort of see some reservoir quality control on the gas as well. In terms of hydrocarbon phase, this is a gas cap reservoir, and you can see a subtle shift in the well site gas compositions at the gas oil contact. And I think there's another slide here. And the predicted GORs of the gas cap and the oil leg are very comparable to what we see in the offset, what we see in the measured data that was that was measured in the PVT lab. Excuse me. So you can see in the oil leg here, in the gas cap, sorry, we're around 11,000 predicted, and that coincides to the measured MDT GORs of 12,000, and then deeper in the oil leg, the measured MDT GORs are around 1,100 scuffs a barrel, and that coincides to what we predict using the well site gas data, which is a really nice example. This is another example a bit further afield. So this is offshore Ghana now. And this is a series of stacked Turonian sands. What's very interesting is the hydrocarbon gas is similar to what we saw on the previous slide, is an excellent proxy for hydrocarbon saturation. There's clearly zones of high gas, and they coincide nicely with the zones of increased resistivity. But we can take the data a bit further now. We can see potential zones of reservoir compartmentalization. So there's a series of stacked sands. This is the upper sand just here. And you see each sand has a relatively consistent compositional signature, but each sand is subtly different from one another, as you can see here. What's interesting is, though, on a pressure gradient, these all look to be in communication. It's only when you look at the compositional signatures do you start to suggest there's the subtle differences, and do you have any inter-reservoir baffles there, and have the pressure differences mixed out, but the compositional differences haven't had a chance to mix out yet, given that pressures mix out more readily than compositional differences. When we move down to a deeper reservoir sequence here, so this is called the EO2 reservoir, we see a thicker sand, which is a better quality, and then above that we see a rattier sand, which is interbedded with some shales and sands. And you see a distinct difference between the compositional ratios between these two sands. And again, are we seeing an intra-reservoir baffle between these two sands inhibiting flow? This well, it was drilled with an oil-based mud, and the PVT compositions, which are the squares you see here, these have been used to tune the mud gas data to match perfectly to the PVT composition. So you can see an excellent match between the C1, C3, and C4 components. The C4 is a bit different, but that's because a bulk correction has been applied to butane, and the iso and normal butanes have not been differentiated. So given that we've used the PVT data to tune the compositions, and the GOR predictions are very accurate, we can use the fact that the mud gas data is recorded continuously from the top to the bottom of a well to try and map the GOR variations within a reservoir. And you can see in the upper reservoir, so the EO1 upper, just up here, the two reservoir zones, hydrocarbon bearing throughout, which you can see on the resistivities just here. The predicted GORs they show a similar trend, but they are subtly different. Again, is this shale here acting as an inter-reservoir baffle? The EO1L sand here, this time all the GORs look relatively consistent. So you'd lean towards saying that this sand is connected. And then down in the EO2, where we think that we potentially have an intra-reservoir baffle, the predicted GORs in the blue are really quite close to the measured data in the red. And again, there's a subtle break in the GOR trend within this intra-reservoir shale just here. So we can potentially use the data to identify compartmentalization within a well. And finally, I mentioned that we published some findings comparing Girasol predicted pay to petrophysical pay in the SPWA in 2023, I think it was. And this is just some high-level findings from that study. So the example is from the Blake field, which is in the Inner Moray Firth in the UK sector of the North Sea. It's quite a complicated field, as there are some minor levels of biodegradation, which complicates the gas data, as you'll see in a few slides' time. Or you'll see it straight away, actually. So this is from a lateral development well, sorry. And you can see the predicted pay is in the right-hand green column, which has more gaps within it, and the left-hand column is the predicted pay from the petrophysical workflow. You see there are high gases throughout the well, as you might expect in or as you'd hope in a development well, and there are some breaks in the lithology with some shale interbeds, and you can see there's no predicted pay in the petrophysical workflow in these zones. But what's interesting, or not what's interesting, is what came out of this study is that in the heel of the well, so this triangle just here is where they began drilling laterally, and in the first 350 feet of the lateral section, there's very low gas levels in all the wells we looked at, and we attribute this to the accumulation of mud and cuttings in the heel of the well, and that's inhibiting flow back to surface. So you have very low gas levels based on low levels of mud and gas, therefore reaching the top side. So the predicted pay is always going to be lower in this zone, and the slide shows it in a more detailed example here. But you can see the top and bottom of each hydrocarbon-bearing sand is perfectly matched with the Girasol predicted pay flags you can see here. And then on the right-hand column is what we use for the GOR. So this is the compositional ratios, and you can see the NC4 IC4 is pretty much absent except in the gas cap just up here. And you can see there's a shift in compositional ratios at this gas cap, reflecting a transition from a gas-bearing sand into the oil-bearing sand. And typically this NC4 IC4 ratio, this is comparing your normal butane to isobutane, and your isobutane is less susceptible to biodegradation. So you can see any ratio in blue lower than 0.55, 0.5 is what we normally look at, is suggested to be in a biodegraded reservoir, and that's what we see here. And the green line, which is the C3 over C2 plus C3, so your ratio of propane to ethane, which is typically what we use for phase prediction, is also very low. And if you didn't know this reservoir was biodegraded, you'd see this ratio and suggest, well, this is the driest gas I've ever seen in the North Sea. But it's dry because you're degrading your C3 preferentially to C2. So you have to use a different type of biodegradation tuned GOR predictions to match your GORs. So this is a lateral well, so we see the top and the bottom of each of these hydrocarbon-bearing sands accurately matched, and then there's just some variation in the gas levels. So we're slightly under-predicting the levels of gas here. This is from another lateral well, and again, I mentioned before, we have missing gas data in the heel of the well, so this is where you're inhibiting mud flow back to the surface. So there's basically the whole of the well is predicted as hydrocarbon-bearing based on the gas data. And that coincides very nicely to what the actual petrophysical assessment revealed as well. So between 7,000 and 10,000 feet, so just here down to the base of the lateral, this looks to be entirely hydrocarbon bearing with a net pay of 3,100 feet, and the gas pay predicted there is 2,990, so very comparable. In the upper section, between 6,467 feet and 6,548 feet, again, this is hydrocarbon bearing based on the wellsite gas data, and hydrocarbon bearing in the petrophysical data as well. It's only this middle zone here between 6,548 and 6,876, which incorporates this casing point in the heel of well, where we start to see a mismatch between the predicted pay from the gas data and the modeled pay in the petrophysical workflow. The right-hand plot here, looking at the compositional ratios, again, we see a shift in dryness and C2 ratios at the contact. So we can clearly identify hydrocarbon contacts based on the gas data. But this is a more nice example of where we see this normal to isobutane ratio being a more telltale factor of biodegradation. And we can use zones where this NC4-IC4 ratio increases to identify zones where biodegradation is lower. So where you see increased NC4-IC4 ratios, your green curve, which is the propane-ethane ratio, increases as well. So these are potentially zones of tight zones, which is what you see here with this increased resistivity. But they can also be zones of lower biodegradation, which is this zone down here. So actually comparing all the wells, so the bottom two plots are the mud gas predicted pay on the y-axis and the petrophysical pay on the x-axis for all of the exploration and pilot wells on the left-hand side, and all the lateral development wells on the right-hand side here. So basically, there was 24 wells in total, like you can see plotted on these graphs here. So in several of the wells, the mud gas data is over predicting pay, and that's what you see just here. And this is where the Blake field has several zones of paleo or residual columns below the reported oil water contact. And given that gas levels are most sensitive to hydrocarbon saturation, there's a mismatch between the petrophysical workflow and the mud gas predicted pay here. So the oil saturation in the hydrocarbon bearing reservoirs is around 80%, but still 20 to 50% in the paleo columns. So that's just an important factor to understand, that there potentially is some deeper residual pay within several wells. Looking at the lateral development wells, now this is where the mud gas is under predicting the thickness of pay, and that's predominantly due to low gas values in the heel of the lateral well. So just before you're going horizontal, there's an accumulation of cuttings and mud in the heel of the well, and it's not quite, and that's inhibiting flow back to surface. And you can see the R squareds for the exploration and pilot wells were about 0.96 between the two methods. I should say, sorry, the blue diamonds you see here are pay flags or gas peaks 3 times above the background, and that's normally the baseline case that we use to determine zones of increased saturation. But we use a 4 times background to try and be a bit more pessimistic on the zones, and sometimes this might be viewed, if your reservoir quality is more of a key controlling factor on hydrocarbon saturation, this might be a good way to determine zones of more robust hydrocarbon pay. So you can see good R squareds for the exploration and pilot wells, and the R squareds are a bit poorer for the lateral wells, and that's mainly attributed to the poor match in the heels of the lateral wells. So that was everything I had. Just under 40 minutes. I hope that's okay. But please let me know if you have any questions, and I'll happily try and answer them.
Hi everyone, very nice talk, very good overview. And maybe if you switch on back your camera, and people can see you. And then I'm just checking questions in the chat. Is nothing so far. So now we have about maybe 20 minutes for people to ask questions. Very good overview, and it's very good, very detailed case studies shown, and they are published, so people can go and read. And the references are also shown in the Force website. So it's very good. So anyone, any question to Lloyd right now? Just raise your hand, and then you can just unmute. No? Olaf, nice. Maybe you just short introduce who you are and which company.
Yes, hello. Olaf Thiessen from Equinor in Hastatt. And I wonder if you have ever tried this in uplifted basins like the Barents Sea, cold and uplifted, the best you can guess for GOR prediction from mud gas, I guess. Oh, you're muted.
Yeah, sorry about that. Hi Olaf, thanks for your question. So in where we think phase separation is occurring, we typically apply the Glasso PT constraints to the GOR prediction plots. I don't know if I've got let me see what I can show you in the background. But what we try and do is, using the Glasso correlations, we try and predict given the pressure and temperature of the reservoir, we'll predict the maximum GOR an oil can be and the minimum GOR a gas can be. And that's really the best guess we can get at the moment. Using the machine learning approach that we're currently developing, we're hoping to improve the prediction in phase separated reservoirs.
Yes, thanks.
Anyone else from the audience? I see quite many people who are working with such topics, from Equinor to Aker BP or others. Any operational geologists in the audience who might be working with drilling? I don't know. Yeah, Corinne, then it's your turn. Maybe also say who you are, which company.
Hello, I'm Karina Høyestebø. I'm working with OMV, Operations Geology.
Good afternoon.
Good afternoon. Thanks a lot for a very interesting talk. I don't have questions right now, but really appreciate your presentation. So thank you.
Yeah, thank you. Feel free to reach out if you have any questions after the talk as well.
Thanks a lot.
So, anyone? You still have time. Nobody? Sure. Let's wait until 45, and then basically we close it at 45 if nobody raises the hand. And thank you again. And then I guess good thing is with the Teams invite is that you can see the people's emails, and then if you have direct questions to Lloyd or Geir, to APT and other things, you can just contact them. Yeah, I guess it's evident. So you can see the emails in the Teams invite. And then maybe all of you had question? No, I don't know.
Hi, I just wonder how do you calculate the temperature correction for the different compounds?
It was mainly done from a large literature review of published. There was a PhD paper that actually looked at the extraction efficiencies of heavier components from gases, from muds, which was the basis of it. And then a lot was just learning along the way, really, using different mud types. And I think then we settled on a standard suite of correction factors that we're happy with. And then what we do then is, in an ideal world, we'd have PVT data to improve it. But if not, we use the standard as a first guess, and then incorporate any of the offset data available.
Yeah, thanks. Really nice. Yeah.
Thank you.
Yeah, but then people, if nobody has any questions, then we don't drag it out longer. So thank you very much for Lloyd again. Very nice overview, especially given your life situation of being a young father. So you have to prioritize other things in the meantime.
Yeah.
And
yeah.
then
Thank you for
thanks
rearranging.
again.
Cheers.
And then just one last thing is that there will be another webinar in 2 weeks' time. It will be also very focused on geochemistry and geochemical production allocation methods, held by our former colleague Torsten Galli. He's at Geolog now, so the event is probably out on the FORCE webpage. And also, if any of you would like to have any good academia or service company or industry focused talk, you can just suggest and organize it with the MPD and NOD together. And also, if somebody would like to take over the leadership of the network from like September onwards, I know that Christoph is probably one of them, but it's usually 2 people that you can volunteer and just send me the mail. I guess from Equinor we are like 20 people working with geochemistry and PSA and mud gas and so on. So would be good that someone from Equinor also joins, probably Christoph from September. I've been doing this work 3 years now. It's very rewarding. You have a big network and you organize these webinars and even on in-person seminars if you would like to. And I think it's in a world when the whole geochemistry and pattern system is kind of shrinking, it's fewer and fewer people. It's good to keep connections and the network alive across companies and universities and service companies. So it's a good event for sharing knowledge, good atmosphere, good forum. So basically that's it. And then if no other questions are there, I don't see anyone, even in the chat. Don't see any. Then we would like to thank you, Lloyd, and also others from APT like Geir, and also Frederick, I see their names, for the nice work. And then if you want to contact APT afterwards, you can just do it later. And then come back 2 weeks' time for the geochemical production allocation webinar if you are interested.